And then we cross the beams and collide the particles. And in those collisions, you're recreating the conditions that were present less than a billionth of a second after the Big Bang.
Scientists at CERN are on the edge of their seats, eagerly awaiting groundbreaking revelations from the world's most advanced and powerful particle accelerator. The Large Hadron Collider, an engineering masterpiece created by the European Organization for Nuclear Research, has illuminated countless scientific enigmas. Brian Cox has just revealed that a startling and unexplainable event has occurred at CERN. During a high-energy test, CERN's experts stumbled upon something unforeseen and potentially groundbreaking. Could this discovery unlock deeper mysteries of the universe, such as miniature black holes? And what is the connection of this discovery to the Mandela effect? Let's explore why this enigma has left even seasoned experts perplexed. Nestled deep under the Franco-Swiss border is an engineering wonder stretching a remarkable 17 miles in a circular configuration. This is the Large Hadron Collider, a colossal ring of superconducting magnets, intricately crafted to accelerate particles invisible to the human eye. The Large Hadron Collider is renowned for its pioneering findings. Here, researchers have glimpsed the realm of minuscule particles, revealing secrets that have baffled us for generations. One of its notable triumphs is the identification of the Higgs boson, frequently referred to as the God particle. This finding was pivotal, as the Higgs boson completed the missing segment in our standard model of particle physics, a framework that demystifies the fundamental constituents of everything we see. Recently, Brian Cox announced a startling new discovery at CERN, leaving the scientific community in a state of bewilderment and surprise. But what makes the Large Hadron Collider so crucial? It transcends the mere discovery of new particles. The true wonder of the Large Hadron Collider lies in its capacity to replicate conditions just moments post-Big Bang, the colossal explosion believed by scientists to have birthed our universe. By colliding particles at speeds nearing light, the Large Hadron Collider reenacts these primordial conditions, offering a snapshot of how our universe might have appeared and functioned at its inception. It's akin to a time capsule, guiding us to the universe's beginnings, aiding our comprehension of its origin and evolution. Post-World War II, amid the lingering echoes of conflict, a group of forward-thinking scientists envisioned a haven for knowledge, where the remnants of war could transform into a crucible for collaboration and discovery. This vision led to the establishment of CERN, the European Organization for Nuclear Research, in 1954. CERN was more than a mere lab. It was a beacon of hope, a testament to humanity's potential when united for a common cause. Throughout the decades, CERN evolved from a post-war aspiration to a bastion in particle physics. It has become a nexus where brilliant minds from across the globe converge to decode the universe's enigmas. CERN's flagship, the Large Hadron Collider, epitomizes its growth and importance. This sophisticated apparatus has enabled scientists to test theoretical frameworks, question established notions, and extend the frontiers of scientific understanding. What began as a small alliance of nations dedicated to scientific exploration has burgeoned to encompass 23 member countries and a multitude of scientists. CERN has led to some of the most remarkable discoveries in physics, from unearthing new particles to spawning technologies with far-reaching implications outside the lab. A critical component of the Large Hadron Collider is its magnets and cooling mechanisms. These are not ordinary fridge magnets or coolers. The Large Hadron Collider employs thousands of superconducting magnets, some bending the particle trajectories, others compressing them to enhance collision probabilities. These magnets are superconducting, meaning they conduct electricity sans resistance, but only in ultra-chilled conditions. Here, the cooling systems are vital, maintaining the magnets at a staggering negative 456 degrees Fahrenheit, colder than the void of space. But why such extreme cold? At these temperatures, the magnets function in a superconducting state, adeptly directing and accelerating particles around the collider ring with unparalleled precision. When contemplating the Large Hadron Collider, envision a colossal, intensely cold ring where superconducting magnets synergistically propel particles at dizzying velocities. This amalgamation of scale, temperature, and magnetic finesse renders the LHC not merely an engineering marvel, but a scientific orchestra, with each element synchronizing flawlessly. It is this harmonious interplay that empowers the Large Hadron Collider to uncover the profoundest secrets of the universe. The latest discovery at CERN has fundamentally altered our perception of modern physics. Brian Cox, a former CERN researcher and a respected authority in the field, maintains a profound connection with the Large Hadron Collider and its ventures into the uncharted. Cox recently stepped into the limelight, making an announcement that has stirred the scientific community. He disclosed that CERN detected something unexpected and alarming. Such revelations are rare, leaving these experienced scientists bewildered, and that's exactly what has occurred. Brian Cox reports that CERN scientists managed to replicate the Big Bang within the Large Hadron Collider. This achievement could pave new pathways for CERN, potentially revealing how our universe was formed. However, this announcement has raised concerns. While the prospect excites scientists, many, including Cox, fear the potential for disastrous outcomes. Venturing into the unknown, particularly in large-scale experiments like those at CERN, poses inherent risks and challenges. Let's consider what exploring the unknown at a facility like CERN entails. Experiments in the Large Hadron Collider involve energies and particles that, until recently, existed only in theoretical realms. Manipulating the universe's basic components might, in theory, lead to unforeseen results. It's akin to opening an unknown door. While most scientists consider these experiments safe, the inherent uncertainty in pioneering science always entails some risk. An illustrative example of these dangers is Russian scientist Anatoly Bugorsky's 1978 accident. While working on a particle accelerator, Bugorsky accidentally exposed his head to a proton beam. Remarkably, he survived but suffered severe injuries. This incident, though not directly linked to CERN, underscores the inherent risks of working with such potent machines and high-energy particles. Another frequently discussed hazard is the formation of miniature black holes. Some hypotheses propose that the intense collisions within the LHC could spawn tiny black holes. Despite sounding like science fiction, scientists reassure that these black holes, if formed, would be highly unstable and likely dissipate swiftly due to Hawking radiation. The likelihood of a stable, hazardous black hole emerging is extremely low. Nonetheless, the concept invokes both wonder and worry. The scientific community's reaction to this discovery has been a blend of fascination and caution. There's keen interest in what this finding might mean for our comprehension of particle physics and the cosmos. Yet there's also a hint of anxiety, as delving into high-energy physics sometimes opens a Pandora's box. Such a mix of enthusiasm and wariness is common in science when on the cusp of potentially revolutionary discoveries. Scientists globally are keenly awaiting more details, ready to analyze this enigmatic discovery. In academic and research circles, discussions are rampant, speculating about the nature of Cox's announcement and its potential impact on the future of particle physics. The Mandela effect refers to a phenomenon where a group of people collectively misremembers a fact or event. Named after Nelson Mandela, as many incorrectly recalled him dying in prison during the 1980s, though he was actually released and passed away in 2013. It's akin to a collective memory illusion. How does this relate to CERN? Here's where it gets intriguing. Some theorize that CERN's high-energy experiments, especially with the Large Hadron Collider, could be causing distortions in reality's fabric. The idea is that CERN's powerful experiments might be creating minuscule breaches or gateways to alternate dimensions. This is hypothetical, but it's an engaging concept to consider. A theory posits that if parallel universes exist, our world might be intersecting with them. During such interactions, some individuals' memories might merge with experiences from these alternate realities. This is where the Mandela effect could manifest. It suggests that CERN might be inadvertently causing these memory overlaps, providing us glimpses into different historical versions existing in parallel universes. It's essential to note that this is speculative and theoretical. CERN scientists are not deliberately attempting to access other universes, and there's no solid evidence backing these notions. But what if the Mandela effect is more than a memory anomaly? And what if CERN's pioneering experiments are unlocking doors to realms previously unknown? This is where string theory enters the discussion. In simple terms, string theory proposes that the universe's most fundamental elements are not small particles, like atoms, but rather minuscule strings. Picture minuscule, oscillating strings all around us. The manner in which these strings vibrate dictates the type of particle they become. Essentially, the universe is composed of these tiny strings, each playing its distinct melody. The concept becomes even more fascinating with the topic of parallel universes. String theory introduces the notion of additional dimensions, far beyond our familiar three-dimensional space. According to string theory, these extra dimensions might be compact and imperceptible, yet they exist, adding layers of complexity to our universe that we never fathomed before. String theory also suggests the possibility of parallel dimensions. These extra dimensions, as per string theory, could be the realms where alternate universes reside. Our universe might merely be one stratum in an immense cosmic structure, and these additional dimensions constitute the elements of the other strata. Every stratum represents a different universe, existing alongside ours but in an inaccessible dimension. Of course, this is all theoretical. We haven't directly observed these extra dimensions or parallel universes, but string theory provides a framework to contemplate their existence. It's akin to a vast cosmic conundrum, and string theory is one approach to deciphering it. Researchers at CERN, among others, are investigating these theories, seeking evidence that could elevate this theory to reality. This represents a thrilling, albeit intimidating, frontier in our quest to comprehend the universe. One of the profound enigmas that CERN has been probing is the notion of concealed dimensions. Gravity, the force anchoring us to the Earth, is a daily constant. Yet, despite our scientific progress, gravity remains enigmatic. We grasp its functionality, like maintaining planetary orbits, but the underlying reasons for its behavior are still somewhat mystifying. It's the feeblest known force in the cosmos, yet its impact is colossal. Some scientists entertain a captivating hypothesis. Could gravity be intertwined with hidden dimensions? This is not merely science fiction, it's a serious scientific conjecture. The hypothesis posits that gravity's influence might extend beyond our three-dimensional existence. Visualize our universe as a multi-tiered cake. We inhabit one tier, existing in 3 dimensions. But what if there are additional unseen tiers? These concealed dimensions could be minuscule and compact, eluding our detection, yet gravity might permeate these dimensions. This could explain why gravity is weaker compared to other forces. It's dispersed across more dimensions than we realize. The Large Hadron Collider at CERN is a sophisticated instrument probing these extra dimensions. Discovering these hidden dimensions would revolutionize our understanding of physics. It's comparable to uncovering a secret chamber in your home that you never knew existed. This hypothesis offers explanations for some of the most profound mysteries in physics, such as why gravity differs so markedly from other fundamental forces. Thus, while gravity is familiar, it might also be a gateway to uncovering new facets of the universe. CERN's investigations are not confined to gravity alone. Quantum entanglement is another enigmatic phenomenon within the quantum realm, the domain of exceedingly tiny particles. Imagine 2 particles so intricately linked that altering one instantaneously affects the other, regardless of the distance between them. It's as if you have 2 magical dice. Rolling a 6 on one means the other, even miles away, also lands on 6 simultaneously. Now, where does CERN fit into this? Researchers at CERN use the Large Hadron Collider to study quantum entanglement. By colliding particles at extreme velocities, they create conditions to observe and experiment with quantum entanglement firsthand. Understanding quantum entanglement could be pivotal in unraveling major mysteries about space, time, and possibly other dimensions. It's akin to a jigsaw puzzle with missing pieces, and quantum entanglement might help locate those pieces. CERN's experiments could provide insights into how space and time intertwine in the universe's fabric and whether hidden dimensions exist beyond our perception. While quantum entanglement may seem fantastical, CERN's research could edge us closer to unveiling universe's secrets that we've only started to probe. CERN's influence extends well beyond particle physics. This scientific titan has spurred remarkable technological advancements impacting our daily lives. CERN's research significantly contributed to developing positron emission tomography scans, vital in hospitals for detecting diseases like cancer. These scans use particle physics to generate intricate internal body images. The technology for these scans was nurtured in the same environment where scientists are unlocking the universe's mysteries. This is a prime example of how advanced science can lead to practical, life-saving tools. Perhaps CERN's most extraordinary contribution is something we use daily: the World Wide Web. The web originated at CERN in 1989, invented by Tim Berners-Lee, a British scientist. Initially, it was a tool for physicists worldwide to share research, but it laid the foundation for today's internet, revolutionizing communication, work, learning, and leisure. From online shopping to video streaming, the web has fundamentally altered our existence. While CERN primarily focuses on particle physics and delving,